Sorry, I don't have the visual for the bread. Is going to be on the video that you get. So volume of slicing. The idea is to find the volume of an object whose cross section is a similar shape over the area. So once again, if I go back to the loaf of bread, this cross section and this cross section, they are similar in shape, right? They're not identical, but boy, they're really close. And if I go to, you know, the very tip, it's really similar in shape, right? That's the idea we're talking about, is each one of these cross-sectional areas is a similar shape. So each cross-sectional area, we're going to do it over an interval. Our integral, our volume by slicing is from end to end, for example, tip to tip of the slice of bread, of each cross-sectional area. That's what A is. A is the cross-sectional area. A is the area here on the shape. Nothing to do with the depth, it's the area of the shape. We're going to take all of these, we're going to take this area and integrate it from end to end. Okay? Does that make sense? I've found that this is the best way to explain it, is doing that. But that's what we're doing. We're taking a cross-sectional area. A of X is the cross-sectional slices. We slice it through, what is that cross-sectional area? And A to B is from tip to tip, end to end of the object we're trying to find. Okay, does that make sense? So the key to this thing is, you got to find your A and B, and you got to figure out the cross-sectional area. And that's the most difficult thing, is figuring out the cross-sectional area. All the ones on your homework are essentially going to consist of rectangles, squares, triangles, and semicircles or circles. So they're basic geometric shapes that you have to find the area for. Okay? First example. And you don't need to get everything down, get the drawing, get the idea. You don't have to. Example number 1, the mathematician's paperweight problem. Classic problem. Mathematician's got a paperweight. So it's base, the bottom part, the flat part that sits on the desk, or on top of the paper, so hold the papers down because it's paperweight. That's the term paperweight. On the paper, lay it down the paper. Okay? Is the shape of the region between the x-axis and one arc of the curve y equals 2 sine x. Okay. Each cross-section cut perpendicular to the x-axis is a semicircle whose diameter runs from the x-axis to the curve. Find the volume of the paperweight. Okay. So we need to figure out a few things. We need to figure out where we start, where we end, and what is the formula for our cross-sectional area. Okay. So this is a graph of the curve. This is essentially the bottom of what we're talking about. That's what the base looks like. Pick it up and look at the bottom. That's what the base would look like. X-axis, y equals 2 sine x. So one bound, that's 0, starts at 0. The sine of 0 is 0. Where is the x-axis and where do the x-axis and 2 sine x cross each other? Well, they cross each other everywhere the sine is 0. Okay, so sine of 0 is 0. The next place that the sine of 0 takes place where? Think about your unit circle at pi. So our volume is from 0 to pi. Those are our bounds. Goes from 0 to pi. Now we need to find the area formula. So here's what we're dealing with. Every single cross section. So every slice of this runs perpendicular to the x-axis, right? These are each the slices. Imagine this was a piece of bread instead of a paperweight, and I'm cutting it with a knife just like I cut the bread. This is where every slice would be, perpendicular to the x-axis. Okay? If I were to take this piece of bread and lay it along the x-axis, how did I slice it? I sliced it perpendicular to the x-axis. That's what we're doing here. Each one of these slices is a semicircle. What is the area of a semicircle? What's the area of a circle? The area of a circle is pi r squared. What's the area of a semicircle? Pi r squared all over 2, because it's half of 1. Right? Okay. We need to figure out what the radius is. And plug that in. That's our area formula. Surface area is what is the area of that semicircle. Well, with pi r squared, what's r? Now, if you read carefully, it says each cross-section whose diameter runs from the x-axis to the curve. So at any location, at any point x, what is y? Y is 2 sine x. This total distance here is 2 sine x. That's the diameter. What's the radius then? 2 sine x divided by 2. Right? If 2 sine x is all the way across the diameter, that means the radius is the sine of x. Does that make sense? So our volume is from 0 to pi of pi over 2 times the sine of x squared dx. Or to neaten it up a little bit, and I do want to show this so you guys can understand a couple of things. My volume is equal to pi over 2 times the integral from 0 to pi of sine squared x dx. There is no antiderivative for sine squared x. It's not an easy one to worry about. So how are you going to solve this? On your calculators. Let's calculate. So you do that on your calculator, and you get the answer. Here's the interesting thing. So you get the answer multiplied times pi over 2. If you leave pi out of the answer, so what do we get? We got 157 something. Divide that by 2, half of 15. That's 70. That should be 7.707. Blah blah blah. Right? I think that's what it works out. We're close to that. No. No, divide it by 2. Don't multiply times pi. Divide it by 2. I want to make a point here. 0.785. So when you do this part here and then divide it by 2, you get pi times 0.785. That is perfectly acceptable answer for the AP people. You do not need to multiply pi times what you got for your integral. Let's say you did what I did, and you take the integral on your calculator without the pi over 2, and you got 1.57 blah, 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 blah. You wrote pi over 2 times 1.57 blah, blah, blah. You're good as long as you're good at 3 decimal places. You do not need to give it fully multiplied out. Okay, it's one of the tricks for taking the AP test. Okay, once you get a final numeric answer, you can stop. You don't have to take that constant out front and multiply it times what you got for the rest of it. You can stop at that point. You may need to do it for a later problem, but for that particular problem, you're done. Okay. Questions on this? Yes?
So does that take into account the length of the paper plate?
Oh yeah, because what we did is we took all of these. Took a whole bunch of them. That's what the integral does. We take its little slice, an infinitely narrow slice that has that area, and then another one, another one, another one, and another one, and another one from 0 to pi.
So it's half circle, so it's like a half sphere?
No, it's not a whole half sphere. At the ends, what's it going to look like on the ends? Okay, so that's the bottom. Your paper, no, hang on. Your paperweight sitting down looks like that when you're looking at it on end. It's going to be a funky shape. It comes to a point because it comes to a point. You have a little half circle, little half circle. You have a bunch of little half circles. If you were to look at it three-dimensionally, you got one side's flat, the other side's curved, but the whole thing's like a hump over from there. This comes to a point, that end comes to a point. It grows a little bit larger and then narrows back down again. Okay? Those are those are where my cross sections are. Yeah, just a random number, because technically how many cross sections are we going to have? An infinite number of cross sections. Right? And I'm really pretty good, but I'm not going to go on infinite number of atoms.
So explain
Took what I got divided by 2. Yeah, and I'm just saying as an example, you can figure out what that is numerically, the sign, the integral, and then do what number you get for that times pi over 2, or you can take it divided by 2 and have pi times that number. Okay, I'm just saying that's an example of what you can do in particular. What did you guys get? 2.43. We can go back and take a look and see what you're doing. Okay? And that's the volume. Not very big. Okay. Your turn. It's not the same. Let's do this. So our bounds are still the same bounds, right?
Yeah.
Okay. So our bounds are still the same bounds, 0 to pi. Problem is, got to find the area. So we're dealing with a right triangle, 1/2 base times height. Okay. And each one of these cross-sectional slices is a right triangle. And it says, what is the base? It says base is the shape of the region between the x-axis and one arc of that. So this is 2 sine x, that's one side, whose height is twice that, 4 sine x. Okay. So what is my area? 1/2 times 2 sine x times 4 sine x equals 1/2 times 2 is 4 sine squared x dx. Yes. Starts at the point, comes up to a point. Once this side of it is flat, and it kind of comes up. And then actually, what it would look like is on the bottom is this. The flat side here would be that. Only each one is twice as high. Yeah, it kind of looks like an odd shaped orange wedge. Kind of what it looks like. Okay, so to be clear, what am I looking for on a test? That 4 sine. I'm looking for that. I'm looking for this. I'm looking for that. That's what I would be looking for on my test. AP, almost identical. 3 points.
Wait, why is it 4 sine?
Maybe 4 points.
What the other two?
1/2 times 2 times 4. What's 1/2 times 2 times 4? 4.
Is it in 4 sine x over 2?
Bingo, that works just fine. Did you hear what she said? She said, rather than write it out like this, she had that. That is bueno. That is fine. Nothing wrong with that. In fact, in some ways, that's better, because one of the things they look for is, did you get the area formula? Did you get the area formula correct in any form? And they will have it as this. They will also may or may not have a simplified version. If they give this, that's the possible correct answer, but you have this on your paper, you're still going to get full credit because they're both two versions of the same expression. Right? They're equal value. They just look differently, but they're two versions of the same expression. That's what they're looking for. That's what I'm looking for. Okay? And then for them, this would be like a 3-point question. Maybe 4. 1 point for the bounds, 1 or 2 points for the area formula with a -1 for each area, and 1 for the answer. Be very careful. They will often say, write the equation, but do not solve. They say do not solve, don't spend forever trying to solve the frickin' thing. Because they will do that often in a non-calculated portion of the test. And you have to write this complex integral that you cannot solve by hand, and students waste forever trying to solve something they can't actually solve. But the directions say, write, but do not solve. Then you write it, but don't solve it. Okay.
How do you get the balance again?
Where's the cross? Where is this equal to 0? Because that's what this line is here, right? This is the line y equals 0. Where do they cross? Okay. Any other questions?